Hey everyone, Miss Butler here. I have a video for you about buffers and more specifically the calculations that we can do with buffer solutions. So hopefully this week you watched a couple videos that just gave you some conceptual understanding of buffers. So there was the Bozeman Science pH and buffers video clip. You should have watched that one. And then the other video clip you should have watched was from the MIT OpenCourseware. So that was Edpuzzle Buffers Part 2. Again, trying to go over the conceptual understanding. So this one looked at Legos. If you have not watched both of those videos, you should go and do those before continuing with this one. All right, so hopefully you have a good visual of what a buffer is and how it works, right? We have the presence of a weak acid and its conjugate base, or a weak base and its conjugate acid. And because we have both of those things present, if I add an acid to it, there's already a base there, the conjugate, to react with it. Or if I add a base, it will react with the weak acid. And so because those reactions happen, we can resist any changes in pH. I'm going to spend most of this video looking at calculations and helping you figure out how to crunch the numbers for these buffer problems. Okay, so just some quick reminders. A buffer is a solution that resists changes to its pH when you maybe add some H plus to it or OH minus. So I have this buffer solution. If I add or stress it out by adding some H plus, the pH is not going to change drastically. Or if I stress it out by adding hydroxide, the pH is not going to change drastically. In order to have a buffer, you need a weak acid and its conjugate base, or you need a weak base and its conjugate acid. Those are the combinations required to have a buffer. How do I figure out what the pH is going to be? Well, we're going to look at the ratio of the concentration of HA, the weak acid, with its conjugate, or the same thing with the weak base and its conjugate. And that's BH. Sorry, mine, I don't know why mine got formatted. This is BH with a little plus. Okay. So by looking at the ratio, that will tell us a little bit about the pH, okay? The higher the concentration of the weak acid and the conjugate, the better the buffer. If I only have a very, very small concentration, we're not going to have a ton of this stuff floating around, which means I can add less of the invader H plus or less of the invader OH minus before the pH starts to change dramatically. So how does it actually work? Well, let's say we're going to add some of this H plus. I have my buffer here. You can see it's the weak acid and its conjugate. Well, if I dump some H plus in there, it is going to react, let's grab my pen. It's going to react with the A minus. So as soon as that happens, it will react with the A minus, and we will still maintain our pH value because we still have some of this weak acid present. What if I add some hydroxide to that original solution? Well, that hydroxide is going to react with the weak acid HA, and in that case, we will be making some more conjugate base, and we can essentially maintain that balance of the pH. Obviously, we're only able to add small or certain amounts. If I dump a whole bottle of H plus, we're gonna run out of the A minus for it to react to, and then we'll see a major change in pH. But the idea is that even adding a bit of this stressor or a bit of this stressor, the pH is only gonna shift ever so slightly, and we can essentially kind of keep that same value. All right, there's a phrase called buffering capacity, which basically tells you how good the buffer is. It's how much H plus or OH minus a buffer can absorb without the pH changing much. So if I have high concentrations of A minus, that means I can absorb a lot of H plus. If I have a high concentration of the weak acid HA, that means I can absorb a lot of OH minus. Okay, what if I want a better buffer? I want to increase my buffer capacity, which would make the buffer zone on my pH curve bigger. So just a reminder, this is a weak acid, strong base titration curve. We highlighted and said that this region is a buffer. So this region, once the titration hits this point, whatever is in the flask is considered a buffer. And so what if I want to make this yellow box longer? Well, what could we do? Well, I could have higher concentrations, higher molarities of HA and A minus. So start with a higher molarity of HA, and then when we get into this region, the molarity of A minus would be greater. Okay, the best buffer happens when the weak acid and the conjugate base are the same, which is the halfway to the equivalence point. So that special point right there. So the best buffers happen when I have high concentrations of HA and A minus, and those concentrations are equal. What I mean by this is 0.1 molar, 0.1 molar, that's a good buffer. 1 molar and 1 molar is even a better buffer because we have higher concentrations and they are equal. The best buffer happens at the halfway to the equivalence point, and that's the same point where the weak acid and its conjugate are equal. So in addition to maybe conceptual questions or multiple choice questions, is this a buffer, what's the best buffer, things like that, the calculation-based questions you're going to see this unit related to buffers are things like this. 1, here's a buffer, tell me what the pH of that buffer is. Okay, seems straightforward. What about if I say, okay, here's a buffer, I'm going to add something to it, an acid or a base. How much did the pH change? So first step, find the pH of the buffer. Second type of problem is you have a buffer, I'm adding something to it to stress it out. Does the pH change, and if so, how much? And then the third calculation question is, I want a buffer at a certain pH. What should I do to prepare it? So we're going to look at one of each of these types so you can kind of use them as examples for your problem set. Okay, so here's the first type of problem. They are giving me a buffer and they want me to state the pH. Okay, so a buffered solution contains 0.5 molar acetic acid, which is not one of my strong acids. There's the formula in the Ka value, and 0.5 molar sodium acetate. So I don't care about the sodium. It comes from sodium hydroxide, which is strong, so sodium does not have any acid-base properties. It's a spectator ion. So what I see is a weak acid and its conjugate base, C2H3O2-. That's the acetate polyatomic. Calculate the pH. So there's 2 options. We can either use an ice table or the Henderson-Hasselbalch equation. For these notes, we're going to do both and make sure our answers match as a way to check. But if this were a timed test, you would choose whatever method you are most confident in. Before we solve this out, I want to remind you, sorry. So these are the notes we took during our weak acid strong base titration video. And we said that this whole region right here is a buffer. So if you look, beaker 3 is the one where I showed you how to solve anything out in this region. So in this case, we added strong base hydroxide to the 12 moles of the HA we had to start. So we do have a buffer because we have HA, the weak acid, and its conjugate and some water. That's the only thing left in this beaker. So how did we figure out the pH, which is exactly what we're doing, right? Once I have this solution floating around, what's the pH? Well, first of all, we did stoichiometry to figure out how much excess HA was remaining and how much A- was produced. Well, in this problem that we're doing, we already know that I have 0.5 molar HA and 0.5 molar A-. Once I know those concentrations, really we're at step 3, and that's where we do ice with the weak acid breaking apart, and we have initial values of HA and A-. So it's basically an ice table with a common ion. We're starting with HA and starting with A-, or the Henderson-Hasselbalch equation. So really, this problem is just like step number 3 of beaker number 3 from our titration curve. So let's take a look. All right. If we do our ice table, it is the acid breaking apart into H+ and the acetate. We have 0.5 molar of each to start. Okay, we know we move towards the zeros even if there's only one, so minus X, plus X, and plus X. And I fill out my equilibrium line. I plus C equals E, so 0.5 minus X, X for the H+, and then 0.5 plus X. My Ka is my products divided by my reactants for the acid breaking apart, and they provided the Ka value for acetic acid. So I'm going to plug in and omit my plus X on the top and my minus X on the bottom because K is small. And so what I see is that I really just get X times 0.5 divided by 0.5. Because these values are equal, we are at the halfway to the equivalence point, right? When my weak acid and the conjugate are equal. And so at the halfway to the equivalence, the pH is equal to the pKa, or we can just solve for X. So we have X right here. Essentially, my 0.5s cancel out. So X equals 1.8 times 10 to the negative 5th. That means that is the same as my H+ at equilibrium. I plug this X in, right? H+ at equilibrium is 1.8 times 10 to the negative 5th. So to find the pH, we take the negative log of that, and we get 4.74. Okay, negative log of the Ka is also called the pKa, and we know the pH at the halfway to the equivalence point is equal to the pKa. Or we could use the Henderson-Hasselbalch. The pH of the solution is equal to the pKa, the negative log of the Ka, plus the log of the base over the acid, B over A. So we take the negative log of the Ka plus the log of 0.5 over 0.5, so the log of 1 is just 0. And so the negative log of 1.8 times 10 to the negative fifth is the same exact answer. So either method works to find the pH of a buffered solution, either ice with a common ion or Henderson-Hasselbalch. Okay, the next type of question is when we have a buffer and we add either an acid or a base to it, and I want to know what the change in pH is going to be. So in this problem, I have the same solution from the previous problem, but I'm going to add 0.01 mole to the 1 liter of the buffer, and I want to see what the pH changes from that buffered solution we just found when we add the NaOH. And then I also want to, just out of curiosity, when I add that same amount of NaOH to water, I want to see what the pH is, what that changes, because then you can kind of see the difference between a strong base being put in water and a strong base being added to the buffer. So let's take a peek. Okay, so the first thing you have to do in a problem where you're adding something to a buffer is do a stoichiometry calculation. So in this particular problem, I'm adding the hydroxide. I don't care about sodium, it's a spectator. So I'm adding OH minus to my buffer solution. Well, the OH is either going to react with the weak acid or the conjugate base. You need to remember acids and bases react with each other. So if I add a base, it is going to react with the acid. So I'm going to add these two together, and when that happens, this H will go to the base to make water, and then we'll be left over with our conjugate. So this is just like what we practiced with our net ionic equations, a strong base added to a weak acid. So when I do my BCA table, I have my 0.01 moles of the OH minus that we're adding. I'm starting with 0.5 moles of the acetic acid. That was because it was 0.5 molar and it's 1 liter, so I know the moles. I have no water, and then I also am starting with a bit of this conjugate, right? We had 0.5 molar of the acetate in our buffer, and it's 1 liter, so 0.5 moles. We set up, we move towards the 0, so there's my 0, so I'm using up and making. And obviously, my hydroxide is going to be my limiting. It's a 1-to-1 ratio, so 0.01 divided by 1, 0.5 divided by 1. Obviously, that's going to be our x, 0.01 divided by 1. So that's our x for all of these, minus x, plus 0.01, plus 0.01. So then we do b plus c to give us a. So 0.01 minus that 0.01 gives me 0. 0.5 minus 0.49 divided by 1 liter gives me 0.49 molar, so moles to molarity. We have 0.01 molar or moles of water, don't really care about that. And then 0.5 plus 0.01 gives me 0.51. And we divide by the 1 liter to get concentrations. So after I add the hydroxide and this reaction occurs, I have new concentrations of my weak acid and the conjugate base. As you can see, the concentrations didn't change too much, and it's because the hydroxide we added was absorbed by the weak acid. That's how a buffer resists the change. There's something there to react with it, so that OH isn't floating around for very long. If it were, it would change the pH dramatically. So now we're going to solve the exact same way we did in the last problem. So we have my ice option. So I have a starting 0.49, that's what we got from above, and 0.51. And so we do our ice table exactly as we did in the last problem, solve for x. And once we know x, we can take the negative log because x is the same as H+, and that will give us our pH. The other choice is to use Henderson-Hasselbalch. pH is equal to pKa plus the log of the base over the acid. Here's the concentrations we just found from the stoichiometry, and so I can solve, and I got the same answer. So either choice is fine, but everyone has to do the stoichiometry step because we're adding something that will react with the buffer. It wanted to know the main change. So on the last slide, we said that the pH of the buffer was 4.74, and we went up to 4.76. So if I subtract those, the change in pH when we added the 0.01 moles of base was 0.02. So that's a very good resistance. Yes, the pH changed, but not a lot. Let's compare it to water. If I add 0.01 moles just to water, not to a buffer, that's really 0.01 molar of OH, which is a strong base, right? So I can take the negative log to get my POH, and then I can subtract it from 14. So the pH is 12, and we know water, it has a pH of 7. So pure water started at a pH of 7 and goes up to 12 when I add the base. That's a change of 5. What the buffer was 4.74 and it went up to 4.76, a change of 0.02. So you can see the huge difference between what a buffer is able to do when we add the same amount of the base compared to just water. Okay, the third type of problem is preparing buffers. So a lot of times they will give you choices like this. So they're telling us that we want the pH of the buffer to be 4.3, and here are the options. So it will be these acids with their sodium salts, because we ignore sodium, so the salt would be like, instead of like chloroacetic acid, we would have the chloroacetate salt, okay? With it, because we know we need the acid and its conjugate, or the weak acid and its conjugate. So it says calculate the ratio of the base over the acid required for each system to give us the pH and what would work best. Well, the first thing, I know that the best buffer is going to happen with a couple of things. The best buffer happens when this ratio right here is equal to 1. And if we take the log of 1, that becomes 0. So really the best buffer is when the pH equals the pKa. So looking at these, if this were multiple choice, I know that I can take the negative log of Ka to get the pKa. I see that we have to the negative 8th and to the negative 3rd. So if I take the negative log of this to the negative 3rd, that's going to give me something close to 3. If I take the negative log of something to the 8th, that's going to give me something close to 8. So I'm going to eliminate these options because the pH, or the negative log of the Ka, is not going to be close to 4.3. If I take the negative log of the Ka for each of these, I get 4.89 and I get 4.19. So far benzoic acid is looking the closest. The other thing they asked for is the ratio of A- to HA required. So in order to get the pH exactly at 4.3, we might not get this perfect 1-to-1 ratio, but we want to choose the one that's closest to 1, because if these are closest to 1, we know that's closer to the halfway to the equivalence point, which means it's a better buffer. It can absorb more acid or more base without changing the pH. So let's look at the next slide, and I will help calculate this ratio right here. So I use this equation. It's my Henderson-Hasselbalch. And I said 4.3, the pH we want, is equal to the negative log, and then I plugged in the individual Ka values. And the ratio of base over acid I called X. That's what we're solving for, and we want to pick the one with the ratio closest to 1. So when I do this for all of them, I get 0.037, 3.86, 0.78, and 1,431. We were between propanoic and benzoic, and as you can see, benzoic has a ratio, that X, base over acid, closest to 1. So benzoic acid is going to be the best. Why? Because the pH is closest to the pKa, and even though it's not perfect, the ratio of base over acid is closest to 1, which would make it the best possible buffer choice. So these problems can be a little difficult at first because you're deciding, well, do I have a buffer already? Am I making the buffer? Is the buffer there, but I'm adding something to it? What reaction should I do? Should I do stoichiometry and then ice, or just ice? So I do realize that these take some practice and getting used to. You have several in your problem set, but there's also another video up above, and it's done by another AP Chem teacher, but he does a fantastic job of talking through other example problems similar to these in your problem set. The link is up there, but it's also on the Canvas agenda for today. So it is totally optional, but as you're working through your problem set, if you need more examples to go off of, I highly recommend you check out this video. He does a great job. Hopefully this gives you a good start to get rolling on your problems.